So, good morning, everyone, and I thank you for this nice presentation. My name is Berk, and I am a professor in Edinburgh Napier University, within the School of Computing, Engineering, and the Built Environment. And today, in the 30-40 minutes, I will try to quickly summarize what we are doing in terms of digital twin and AI-enabled platform that we have, some technical aspects that we have, and try to give some use cases. This is the outline of my talk. In the first part, I will briefly introduce you my lab in Napier, in Edinburgh. And I will briefly talk about digital twin. I know we are all aware what is it and about its market, but just a brief overview. Then I will talk about our digital twin research, what we are doing, what type of use cases we have, what are the current projects that we are going on. Then a bit focusing on the platform that we have, because this is one of first in its kind in terms of academia, not in the industrial wise, but in the academia, we have a platform in Berk. So I will try to talk about the system architecture. I wish I could have like a demo in the morning. I tried in the hotel, but due to some VPN things, I couldn't connect to Edinburgh for some reason, because we have also some real-time servers back in Turkey as well. It's a huge, I will talk about that. It's some kind of related things. So you know the Murphy, when you want to connect, you cannot connect. But I got prepared for this, so I have some videos. So we are good to go. We will pretend that we are gonna run this platform, and then I will show you some kind of use cases. This is me and my lab. Here, I always say the most important part of the slide is the right part of it, which is the real heroes of my lab, my current research group. I previously graduated like several PhD students, like 7. The last one was in the last month, and the new ones are coming, and we try to produce as much as we can. I'm also involved with a Turkish company in a consultancy manner. This is one of the biggest cloud company in Turkey, and they are providing us some kind of in-kind support for their real-time servers. And these are some kind of an outcome, like maybe 30% of it in the last 3 years about digital twin platform and real-time communication of digital twin. I am not a simulation person. I'm mostly in the computer and the communication engineering part. We are doing like the real-time communication aspect of digital twin. Okay. This is an easy one. I mean, you can just do a ChatGPT, not Google these days, as you know, and then see all those things. I didn't refer to ChatGPT, but this is from them because it also steals from the other things, as you know. So if you think about what is a digital twin, it's the virtual representation of a physical aspect. Okay, for us, it means that you will have 2 monitors. Of course, you will have the physical aspect here. This physical aspect will be transferred somehow using real-time data stream to one of the monitors. You do the replica, and then you can of course have we start to have some holograms with the real one, and then try to in the second monitor because it's twin, you try to come up with some kind of forecasting, optimization, what if analysis. You know all those things that when you say which purposes you can use digital twin. These are the classical bullets now for us. Try to come up with some kind of a real-time replica, and then real-time forecasting of the aspect that we try to twin. This is some kind of an example. In the last December, I was in the lovely Kuala Lumpur in Malaysia, and as you can see, this is the Petronas Tower, which is not a digital twin, but a real twin. But why not a digital twin? Because it doesn't. This is the first one, and the second one is the same. It doesn't act as a forecasting. Okay, I didn't just put it because it's a nice picture. I just tried to emphasize that in a digital twin, you have to have the second one as the future forecasting of the real one. So you have to get crazy with the second one in order to understand what is going to happen next. Okay, so you know this movie, which is not a digital twin, which it's augmented reality or virtual reality, whatever you call it, but not a digital twin. I was quite having a friend fights for this because people they think that this this avatar is the digital twin? No, because in the real life, this guy is laying down. But in the virtual world, he's a hero. Okay, so he should be hero as well there. Then I'm fine if he can. But in that particular scenario, this is not the case. Okay, but this one, which is the first place that the real digital twin showed up, where it was in NASA, and they tried to mimic the real movement of the rocket. Of course, not the real one, but like in a simulation environment, while this guy is actually going up, they try to also follow him and then try to understand what is going to happen in the next 3 seconds, 4 seconds. Okay, so they are actually monitoring the real event. Moreover, they try to see what's going to happen. Actually, here in the last 2 seconds, it's not difficult to imagine. So it will go up. It will continue to go up, obviously, but just to see what may happen, what about the health of the astronaut, etc. This is some kind of a real digital twin. Okay, so let's keep in mind that this is the scenario. So you have 2 screens. In one screen, nothing new. So there are lots of free monitoring tools for this. Okay, so you just get the data. You can monitor it in real time, and there are really sophisticated things, the sophisticated products for this. And now here it comes to the funny stuff, where you have the second screen. First of all, you have to have everything that you had here, there, plus you have to, as I said, get crazy somehow. You have to do some kind of real-time simulations, real-time what-if scenarios, real-time optimizations, real-time recommendations, or any kind of data-related things. Okay, so this is where the challenge comes into the scene, because this has to be with a data streaming. So you have to do real-time AI optimization, for example. Okay, if you have lots of data, you can have a perfect prediction, but you are going to lose time. You are going to have a shift. Okay, so you have to somehow understand the latency there. For example, we have a patent application just approved the first stage in US patent. So you have what is called an age of twin. So your age should be quite like young in terms of the twinning. Okay, so you can have lots of data, you can have huge real-time servers, a perfect forecasting for the next maybe 3 hours. But I mean, whenever you predict, you predict that moment, the real one will already go to somewhere else. So you have to balance the reality with your future. This is where the digital twin comes into the scene. Okay. This is not my sketch, by the way, but it looks very good. So these are like terminology that we all know. We have a 3-layer architecture. You can have 5-layer architecture as well if you also get these 2 things. Like you have a physical space where I am also in. Like you will have the IoT environment, 4G, 5G based connected environment. We can have LoRaWAN. We can have Wi-Fi. You have several connection technologies that you can use to grab data in real time. Here, we mimic this, which is also something that has already been done. Okay, you can try to this is the first screen, if you imagine. So you try to just replicate whatever there is here, and then try to analyze with your Gauge, with your dashboard. And here, the second screen comes into the scene, where you have the service space. Okay, what is the service space? Anything that you can imagine, but as long as you are being connected with your virtual one, with the real one actually, and then try to give feedback into it. Okay, the feedback is another important issue here. I mean, you can either feedback to the people, or you can have feedback to the sensors, make them become like actuators, and then open the door. Actually, I will try to show you some kind of examples that we have. No need to, I think, mention this digital twin market size nowadays, but just to refresh our minds, it's quite a huge sector all over the world. Actually, it's gonna, when I first jumped into the digital twin sector, it was in 2020, and then we were all trying to switch whatever has an IoT sector to move to the digital twin sector, which is the case actually today. So several companies, mostly in manufacturing, agriculture, automotive, energy, healthcare. I mean, I will stop reading it, but several companies in those sectors and much more. I mean, they're trying to switch their platform into a digital twin enabled platform in order to see in real time their system and then try to have some kind of predictions. Okay, what if analysis recommendations. I keep saying this several fancy things again and again because this is where the digital twin benefits comes into the scene in terms of industry, at least. AI has a huge importance for us. Why? Because we are dealing huge amount of data. Plus, we are dealing real-time amount of data. So if I keep collecting data from this room, for example, it's good for me, nice for me, but I can have like a delayed version of my prediction. So I have to be quite intelligent and do this data collection in an intelligent manner. Okay, as you know, in big data, we have lots of V's, right? For 4 V's, 5 V's that you can collect the velocity, you can collect the different types of data features. In order to collect the data in an intelligent manner, you have to do some kind of pre-processing as well. So AI starts to be with us from the first layer up to the third layer. In the first layer, we try to collect data as intelligent as possible. We try to do the virtual space as light as possible, so I can change it quickly. And then in the third layer, I try to do the service layer as accurate as possible. Okay, all these things comes with this AI book. Okay, like either supervised, unsupervised, deep learning, etc., etc. Okay, so we are good as the group. We are good AI users. I am not the one producing new AI algorithms. I wish I was, but I'm not. But we are trying to use the AI in our algorithms a lot, and then put those algorithms into our real-time protocols to produce new ones. We do those things, but AI has a really huge importance in our digital twin sector. Let's switch to the research that we did. I will be quick on that. If you want to have more information, don't hesitate to contact me because there are lots of information here. All the slides, the next 6-7 slides, there are huge papers and projects behind it. So I will try to just be quick and then I'll try to put all the fancy figures here, but try to summarize it. The first one is AI-enabled edge communication for sustainable net zero transport. What we do basically, we mimic one road, okay? This is Edinburgh. So we didn't do actually, so we have some kind of municipal with Edinburgh try to get real-time data. But for when we did this project, we were using some simulation environment, okay? So with Sumo, if you know, in the vehicular network industry, so we have this kind of data in the physical environment. We mimic the digital twin, try to map as we have all the movements of the vehicles, and try to come up with CO2 prediction, risk zone identification, like what if analysis with a scenario maker, what is going to happen in the next 15 minutes if all this traffic goes like that. What about closing that lane? What about closing that road? What is going to have effect on the net zero policy specific to the municipality or to the government, etc., etc. This kind of things that we were doing with that project. Similar one, but with the EU support this time. So here, instead of like mimicking the whole network topology of a transport topology, we were mostly focusing on the relationship among cars and try to keep distances between each other, or try to turn one of them left, one of them right, in order to have a stable CO2 emission, in order to have a more green or less congested road, etc., or have more LEZ, like low emission zone road in the streets. We try to come up with different types of mobility solutions. This is the first project that we got 5 years ago, back when I was in ITU, Istanbul Technical University, back in Turkey. This is the study of ITU. So we had drones, and we tried to we were those drones, and we were just flying them and try to balance their altitude, like try to put them in the same altitude, try to make them similar attitudes in terms of turning, twisting, or any other kind of drone moves that you can have. And while we were trying to make these guys move, we were first trying to forecast them in their digital twin version. Okay, so try to first make the drones all flying, get the data in real time, do some kind of a small forecasting, and say that okay, this drone will run out of battery in the next 5-10 minutes. What about like lowering him down? Or these two guys, they are too close to each other, because as a scenario, we said that these are all flying base stations in terms of covering the terrain. So what about putting them as far as possible to have less overloaded areas between this one and this one? So we tried to somehow move the drones using the digital twin forecasting technology, and then give those order backs like a feedback mechanism to keep the constellation as long as possible. Like the duration of the drone base stations stability was the main idea of that project. BTS Group was the main actor here, while providing us their platform, their real-time servers, together with some other colleagues. We had several papers published, and then there is another version of this that is going on now in my group. This is another one, like a disaster resilient mobile communication. Basically, what we are doing here, we are now in that project, we are predicting what is going to happen in the next 3-4 hours whenever a disaster happens in a particular area in terms of communication. Where to put new on-the-fly base stations. If you have an earthquake, so what's going to happen in the next 5-10 minutes, or what's in the next half an hour? If that area is out of connection, what type of drone you should fly, what type of mobile base station you should put there in order to be sure that you are in the good coverage area. This is another interesting digital twin project that we have. In that one, we are trying to cluster the high altitude platform devices, planes, not drones, which are lower altitude platforms. We are trying to cluster them and see what is going to happen in the next 5-10 minutes. What does this mean? Is that we collect the real-time data. In that case, it was free, so we are good to go. There is a small video as well I'm going to play. This is the platform anyway, the first time you see here. So this is as you know, this is the map of UK. So at the time of that video, these are taken in an open manner from a data set. All the planes are really flying at that moment, and then we get their altitude, we get their position, we get their bearing, all the data that we can get, and try to the first screen here, which is the real-time scenario of what we have here, and then try to predict the clustering version of those guys according to their altitude, their speed, their direction, and then say that in the next 10 minutes, up to 15 minutes, we went in that project, up to 10-15 minutes, all the planes, cruise level, all the planes that are in that cluster can use, for example, satellite connectivity in order to provide a better in-flight connectivity. The whole challenge comes to us, actually from at that time from Turkish Airlines, that in all the airlines, all the big airlines, they do this. So they try to provide high level of internet connectivity during the flight. Okay, this is the whole idea, but they couldn't because of the connectivity issues, because each plane has like a limited bandwidth because of the antenna. I am not the expert, they told me. and how to switch between those antennas, like either the satellite antenna or the ground antenna or the antenna that they can use from one plane to another in the same level. So we are trying to give this recommendation engine for the next 10 minutes, saying that if one plane is in cluster 1, we can use ground antenna or ground communication to have a better connectivity. Better connectivity is not, it was not my decision. They told us, the expert told us that in order to have a better connectivity, actually 50 kilobit or 100 kilobit per second is enough for them, which is nothing for us. But yeah, this is okay for a plane at that moment. Cluster 2 can use satellite, cluster 3 can use ground, cluster 4 can use air-to-air with another one in order to get a higher level of bandwidth. Let me try to. Is it playing? I don't know. There's a video there, but I don't know if it's playing. I don't know. Yeah. If it's not playing, it's okay. I mean, in the video, it's supposed to, those clusters are supposed to change. Yeah, there should be a play there, but somehow it didn't work. Yeah, you can. No worries, no worries.
Yeah. Cannot play media, it says.
Okay. Yeah. Usually, I mean.
Sorry.
Yeah, no worries. Just what in the video is that these guys, these small dots were moving. Imagine now that they are moving. And then here they're trying to change the clusters. Okay, this was all it does actually. But this whole small moves requires lots of background research and then lots of papers and projects behind it. But here, this is the final product that we had. This was what we called as a platform. This is the Royal Society project that we have with the air quality monitoring in York. So what we are trying to do is that there's some kind of real-time and simulated mock data from the environment and then come up with new prediction in terms of air quality, what type of air quality levels you can have in the next X10 or XY minutes, etc. And this is again the screen that we have. This is an interesting project that we have been through. First with a paper, and then we converted to a project to submit. Actually, we will submit one of this to the US as well, to the Naval Institute. Anyhow, so what we try to do is that try to grab some information and then predict the movements of ships in order to approach in a better way to a port. What was the challenge behind it? What was the idea? The idea is that they can grab those data, no problem, but this data is quite vulnerable, and there are lots of anomalies. So they try to, I mean, the bad people, the malicious people, they try to reroute the ship instead of a port like 2-3 meters shifting, so that the ship can hit to the ground. It can damage. It can have lots of damage. So this thing, I had no idea about it because I'm not a naval person, obviously. But this is really so important for them. They try to come up with some kind of an anomaly detection of this data collection. So we collected with the cybersecurity aspect and with the digital twin in order to have a digital twin approach for this type of challenge. This is the ground version of the previous case. This is the map of Turkey. And these are the real routers, the real spaces, real location of the routers. and we managed to get some kind of real data, of course, anonymous data. We did lots of dealing with the Turkish Telecom. Maybe you know it, maybe not. This is like the biggest operator in Turkey, like the British Telecom here. So they had the willing to give some data to us from their routers, but of course it took some time for us. And what we did, try to understand the anomalies that may happen at each and every router. Okay, from each and every card, like interface card that we can grab data. Okay, so this was the main idea of this work, was try to have the anomaly detection for autonomous networks. This is again related with the vehicles. Like since we can grab data way a bit easily because of the simulation environment, we try to have anomaly detection for Internet of Vehicles, like network-aware attack detection, vehicle-to-infrastructure communication. We try to monitor here, and to have attack classification, network classification, and then try to verify all the threshold for triggering an alarm for us. And the last part, this is the platform that we have. Not this behind, of course, background. So this is in our, we call it control tower back in Berk in Edinburgh. And we try to like have some kind of predictive analysis, recommendations, what if scenarios, and real-time monitoring. We recently got the an IEEE award for this, like a student project award, because everything started with a student project with these three ladies. And we try to like have more and more applications, but not in the industrial level. We try to give also the research-wise of it, which is the real-time communication, real-time data capturing, and like real-time digital twin version. So how we do that? Okay, we try to have three layers, as I said. In the first layer, we have data. We have different data formats from different IoT devices. We can have historical databases, and we are just collecting them. Once we collect them, if there are different types of data, and if you have huge data, the best thing to do is to use knowledge graphs to build the virtual layer. You can also use like data streaming and distributed processing from different types of services. And finally, in the service layer, we can come up with different types of scenarios. In the communication, what is required, like how you can capture the data from different technologies. Here, we are going a bit like a theoretical. We can use like real IoT environment, real Wi-Fi or Li-Fi, or LoRaWAN, or some kind of a 6G simulation or emulators. This is a known communication protocol, as you all know. This is also known. This is our protocol stack that we have built, like we call it T6Conf. It's a huge research behind, try to give a layered architectures for the digital twin. And here is an example of the protocol stack that we have on the left-hand side. And this is, since you are designing a network protocol, you need to have a sequential diagram. So you have different types of message exchanging between each and every node, like the real device, the virtual device, the service layer, and then back and forth. All these different types of message, we have them ready as an RFC. Even we have an RFC for that, and we have submitted for standard application. Let's see what's going to happen. But we try to see here different types of message formats and different types of connection formats. The data streaming and the distributed processing part of our digital twin platform is mainly the answer of how the data is processed. So data can come from different formats. This is the beauty of the graph database that we have. It can be structured, unstructured. It can be static, semantic, or dynamic characteristics, and it can be processed under real-time constraints. Here we are using microservices. We can use like different types of message brokers. We can use like intensive data ingestion. We call it like in-memory keys or value stores. And this is the whole architecture of the data streaming part. Different types of brokers. For example, this one is Kubernetes, coming from like key value store, and then you go to the database. The main idea is that we try to be as quick as possible in order to process the data. The whole play here is the whole motivation, the whole hidden agenda for us is that to do it as fast as possible. That's why we are using microservices, for example. So if you don't use microservices but do the normal virtualization, things can go a more accurate way, but in a more slow way. So you need to do it in a more quicker way. So we are trying to optimize all these different types of software engineering muscles that we have. This is the knowledge graph. I'm sure several of you already know what is this and how it is good for us, how it is bad for us. It is not good for real time, which is one thing that is, from the beginning, I was saying real time, but since you use graph database, there is a conflict here. Actually, there is no conflict. This is to store once you are done, but you keep being done every 5-10 seconds. So this repetition is a challenge for us. You got me? So we try to build the graph. We are good. After 10 seconds, another graph. After 10 seconds, another graph. This is a huge overload for us. So, and this is a challenge. This is a research question. 3 PhDs are trying to solve this problem. Either from the communication perspective, they say that instead of storing everything, what about making an intelligent communication? Or they try to store it, they try to solve it, making an intelligent storage. Anyhow, so this is the graph database that we are using, because once this graph is done, your life is quite easy. You don't care about the nodes. It can be JPEG, it can be HTML, it can be CSV, it can be doc. The relations are important. Okay, the relation between me and someone bring everything to me. So in a really quick manner, you can grab the data, as long as it doesn't change, in which it changes. This is the challenge that we have actually. This is the comparison between graph databases and the normal non-SQL databases for us, for us to motivate to switch to graph one. And then the last part of it, I'm finishing. This is the platform that now we try to imagine that I directly connect. I couldn't. I will just run the videos. This is the platform. What we do here in our campus in Turkestan, we really have this kind of, in some rooms, like sensors. We collect data in real time. Once we collect the data, we just have the data streaming, and at here, for example, 904, the room, the CO2 level of the room, according to the heat map, looks like this. Means that we are fine. There is no particular alert that we can have, meaning that this part is quite green. There is not so many people, or they don't breathe. I don't know. Somehow here it's okay, but if you keep the door open and if you keep the people coming or whatever happens, 3 hours from now, this is 9, this is 12, the room will become like that with 98 like accuracy. So it's alerting me, saying that okay, I need to close the door. So now it seems okay, but if they keep with that level, according to data that I grab, obviously, my data can be wrong. This is another story. This is another research. But according to this scenario, this will happen. And this is the feedback. Okay, some kind of an alert that is given to me. And moreover, in the testbed that we have, we are also transforming all those sensors into an actuator, like by just connecting them with. I like those things. By the way, in my master time, I was also doing those kind of small sensor experiments. So we try to connect with a motor so that the sensor can also open the door, close the door, let the switch on, off, etc. So this kind of autonomous things can happen. This is not the first time that you see. So there's a huge autonomous industry going on, obviously, but having those kind of future predictions with a digital twin is some kind of an add-on that we are doing. Okay, so this is the example with the smart room. Yeah. The video. Oh yeah, it's playing. Yes. You see the. Is it? No, I stopped it. Okay. So in this part, you also see the reality with the green and the yellow one with the prediction, and you see this is the reality, and this is also the future, and you see the time is also moving. You can see some kind of a map, a heat map according to these two rules: digital twin, first screen, second screen. Not like an avatar that is lying down, but is the reality. They are both in the real time. Okay, this is the catch. I will keep giving you these things, and I will be done. This is the previous example that I have. I don't know if this is a video. Yes, it is.
Codec unavailable.
Okay. Anyway, you see the previous, so this kind of clustering effect that we had again. This is the wind turbine example. This data is not new. This was open and free one. We use this. As we all know, since we are in academia, as long as you refer what you do, we are good to go. But in terms of the industry, so when I show this, they directly ask me, is this a real data? No, it is from Kaggle that we took. But the good thing is that if you give me the real data, this will work. Okay. What is gonna work? Well, the prediction of the energy. This is the prediction one. This is the predicted, and this is the real value. I am predicting this type of movement. Of course, you also see that my current prediction is not the perfect, so you should also take this into consideration. Okay, I'm not matching it previously, so I will not match it in the future as well. So there is the accuracy is not 98, 99 here, but this is a challenge to do. Actually, this is something to discuss. This is something to improve. This is just a platform to play with. Okay, this is playing. This is the last one. Here you first estimate the traffic, and then you say that if the data keeps coming like that, this is the estimate. First look at this, and then according to this estimation, I am fitting the physical environment in order to be free, in order to be more in a better than less congested way. Okay, again, two screen. One is the estimation, one is the fitting back to the reality. Okay, in the previous scenarios, I was showing you the physical one and then feeding the virtual. This is the inverse now. I am first doing the simulation and see things works, and then if it is okay, I'm giving you to the reality. Okay, because this is also another important aspect of digital twin. We want to use digital twin in order to have give some strategies. For example, what if we have divided this room into two? We don't know what's going to happen. Let's divide it in our digital twin. Give me some real-time data. Let's see what is the result. If we are all happy with the result, whatever result we have, then we will divide. So either we grab the real-time information and then simulate the future according to real time, or we simulate the future in advance and then try to give you feedback saying that this looks okay with 95% of accuracy, do it or don't do it. With that, I think I will be done. Yes.